Hi, everyone, and welcome to PyData Global. We're excited to have you join us. Please feel free to use the chat to connect with fellow attendees and share your thoughts during the session. If you have any questions, please post them in the Q&A tab, and we'll address them at the end of the session. So for this session, I have the wonderful pleasure to welcome Shreya Khurana, who is a data scientist at Intuit in California. Shreya also works on the anomaly detection capability that tracks the authentication and business health metrics at Intuit. So please provide a warm welcome and take it over, Shreya.
Yeah, thank you, Patricia, for having me. Hello, everyone. I'm Shreya, and today I'm going to be talking about real-time series anomaly detection in production. Um, Before we get into the weeds, a little bit introduction about myself. I am a data scientist at Intuit. Like Patricia mentioned, I work on anomaly detection. Um, but prior to that, I was working within GoDaddy. It is a website domains online presence company that helps businesses go online, right? Over there, I was building deep learning models to improve recommendation systems. I also have a background in statistics, mathematics. I graduated with my master's from University of Illinois. Really cool place if you've been there. But in general, I am a Python and data enthusiast. I enjoy sharing my learnings with the community at various conferences, meetups, etc. Before I go into the actual work, I do want to thank my team. So my team at Intuit comprises of a data science team as well as the identity analytics team. This work would not have been possible without them, and I'm really thankful and grateful to them for giving me this chance to present here. So before we talk about, before we get into the real details, I just want to ensure that we have the agenda set for this, right? So this talk is about, well, first, time series data, right? Detecting anomalies within time series data, but also it's set within a real-time context and then deploying everything in production. So if you attended this conference since yesterday, you might have also heard about other presentations on time series models, especially set in the context of um, foundational models or these really language sort of models which have inspired time series to build on really large models as well, right? This is going to be a little different. We're going to be talking about anomaly detection, and we are going to be putting all of this in a real-time context and talking about certain tips and techniques on how you can basically implement very simple things, but that are really effective in a real-time pipeline. So I'm sure all of you are very familiar with time series, right? It's nothing but something that is measured across a period of time. And the same thing is measured at different points, right? It can be every minute, every hour, every day. And sometimes this data exhibits behavior like trend, like if it's going up or if it's going down, or seasonality, whether there is daily, hourly, weekly seasonality, right? The applications are everywhere around us. It's in marketing. So if you are modeling, for example, the sales of iPhones and you have a promotional period, you can obviously expect this seasonality to affect your forecasting. You have weather, we have temperature, rain. On this first graph you see over here, this is the air quality index of a city that I was born and brought up in, Delhi, in India. And we see that there is seasonality to it because, well, pollution levels rise and ebb during certain periods of time, depending on, for example, agriculture patterns, whether there are crops burning or there is a vehicular pollution in the air, right? Basically, you can also use it for any other KPI monitoring. You're monitoring your unit tests. You're measuring something within each time your pipeline is run. Or any sort of monitoring system. It can be your business KPIs. It can be any metrics that you're interested in, right? In health, you have, for example, cold and flu. You expect cold and flu to affect during a certain season. So you also have cold and flu products that are basically sold more during that period, right? So all of these things have a pattern, and the best thing about having a pattern is that you can predict them, right? So that's what we're going to be talking about today. And how do we detect anomalies on time series data, right? Anomaly is basically just something that is really different from the expected or the usual. If you have a really stable time series, right? So for example, something that stays within a range of 1 to 10, if it goes beyond a 10 threshold, then you know that can be actually classified as an anomaly. Well, if you have something that's simple, that's great. We don't need to get into any of the other sophisticated things we're going to be talking about today. But more often than not, this will not be the case. Um, so one thing that I do want to point out here is that if your data set, even if your historical data set is not simply defined within a range, if you have a lot of history, right? If the data set you think is simple and predictable enough, there is no need to get into all the forecasting part that we're going to get into, right? You have a historical data set, you know the expected value that you want. For example, if you are predicting day by day, if you know already what your next day should look like, for example, you just make a simple prediction like my next day should look like my prior day, right? Then you don't really need to basically look into all the forecasting methods. You can use all the tips we're going to be talking about, and that part we're going to be discussing here. We want an algorithm to detect anomalies with high precision. And you get anomaly scores, you detect, voila, you have your anomalies. However, where some forecasting framework is helpful is if your time series is really more complicated, right? You forecast to get the expected value, because what you want is to detect something that is really different from the expected. But for that, you need to know what your expectation is, right? So that is where we're going to be using a machine learning framework or some forecasting framework. You get the forecasts, and the approach over here is that you model the residuals. Residuals are nothing but the difference between your data, your incoming data set, and your forecasts, right? So for example, for the next day, you're predicting something like a daily prediction, right? So you have for the next day, the incoming data set as well as the forecast that you predicted today. You calculate the difference, and you see if this difference is large enough for you to actually warrant an alert, right? So, and now that we get into this pipeline, we need two things. We need some forecasting framework, and we need to discuss what algorithm techniques we can use to basically have all of this in production in a really robust manner. So let's get on with the first part, that is NeuralProphet. NeuralProphet is a machine learning forecasting framework, right? You model time series data. It is a further advancement from Prophet, which if you're familiar with time series, you must have heard of, right? Um, but why it's really popular is because one, it works at scale, right? And two, it's very simple to use. When I say it works on scale, what I mean by that is, let's say you have a time series where you're explicitly modeling the prediction with the last 100 or 200 or thousands of values, right? In classical time series model, this part is called autoregression. And in statistical models, this really does not capture the long-term dependencies really well. So this is why NeuralProphet, which is like a bridge between deep learning, machine learning, as well as statistical methods, was introduced. It is very simple to use. There are tutorials. Everything is available online. Feel free to go with them at your own pace. But here, what we're going to be talking about is just very simple things that you can do, and why I find this framework really cool, right? So if you have your data set, and this is a simulated data set, I provided the code to do all of this at the end. So feel free to go at it on your own pace as well. But like all black box frameworks nowadays, right? This is a matter of few lines of code, right? You take a data set that has just two columns, your timestamp and your column that has the actual values you want to model, right? And you fit it, you predict it, you can easily see a plot of where your forecast performs well, whereas where your forecast does not perform well, right? But one of the cool things that I find about NeuralProphet is its ability to actually model parameters. What I mean by that is, for time series, you have certain parameters like trend, different kinds of seasonalities, right, that affect the final prediction. So in NeuralProphet, you don't just see this at an average level, right? You also see this at an individual level, right? So if you're modeling, if you're predicting for a single observation, you can go and see why this prediction is the way it is. It's not a black box. You can see the contribution of trend, different sort of seasonalities like yearly, weekly, daily, and you have a sense of why this prediction is so large or so small, and you can change your parameters accordingly to make it more accurate. The second cool thing that I find about this is its ability to model custom events, right? So in this time series, for example, again simulated, you see that the black scatter plot over here, these are the actual values. During two periods, which are encircled here, you see these values are going down, they're decreasing. However, the model, which is shown here in the blue y hat one, it does not really capture this downward trend really well. And especially during those periods, it kind of smoothens it out. You can see that there's a slight decrease, but it doesn't really model really well, right? So once you sort of have that information, you can actually feed that to the model. The simple way to do this is that you provide just certain periods to the model and say that, okay, this is the event that I'm modeling. In our prior case, this was because of, let's say, Thanksgiving or Christmas or New Year holidays in the US, right? So you can model those periods explicitly, and you don't need to tell the model how to like how, if something is really different, for example trend, you don't need to provide it exact details, you just need to provide it a specific periods. And then you can see here, after just providing those specific event timeframes to the model, we have managed to actually fit the data really well. And for this, you can define any number of events. It's purely scalable. And you can also like manually just inspect your time series to know that it's actually doing what you want it to do. Here, now we're going to pivot. And so far, we've talked about NeuralProphet as a forecasting framework, right? The reason I'm pivoting now is because we're going to talk about some of the algorithm techniques and to detect anomalies. And after that, I will bring all of this together so that it makes sense on how you go from end to end. But for this anomaly detection piece, so far what we have is just time series data. We've learned how to forecast, right? For now, everything that we talk about in this section, um, you don't really need to have the forecasts, right? These are just purely your techniques to have a robust real-time pipeline. For that purpose, this is again a simulated data set that is minute by minute. So you have a span of 2 weeks going from 1st November to 15th November, right? And you have an observation for every minute. Um, and if you're detecting anomalies, you want to know or you want to have a score, right? Usually, if you're familiar with this domain, you know, you must have heard about z-scores. If you've taken a high school statistics class, you must be familiar with it as well, right? So z-scores are a way to determine the extent of an anomaly, or basically how far a data point is from the average. And when we say the average, we mean some period in the distribution or the whole distribution, right? Usually, z-scores are mean-based. What I mean by that is that the average that we're talking about here is the mean, right? And but not we don't just need a mean to figure out a z-score. We want to figure out how far it is, but we also want to put it in the context of the distribution. Because let's say you have two very different distributions, you want to be able to compare the z-scores within them. So the way to do that is that you normalize by the standard deviation or the spread of the data, right? This is like a very familiar way. This is the easiest way people have used anomaly scores, right? Um, but one, but the interesting fact over here is when people talk about anomaly scores, no one really thinks about where are you calculating the mean and the standard deviation from, and that is where the discussion on look back period comes across, right? So look back period is the period in your historical time series on which you look at to find how your non-anomalous or your distribution should look like, right? So the easiest way, for example, is that you look at the entire time series data and you say, okay, I have the mean and I have the standard deviation of this entire data set, right? However, the reason why we're doing this is to basically look at how your non-anomalous distribution should look like, right? We're detecting anomalies. We want to know how different non-anomalous periods look like so we can accurately detect an anomaly. So within this look back period, we actually calculate our stats like averages and spread of the distribution, right? In the case of z-score, we calculate the mean and the standard deviation. But now what period should we actually look at? How do we know this is a good estimate of our distribution, right? One thing, again, like which might be interesting to note over here in this data set is that you see it exhibits certain form of seasonality, right? So you see that there is really high volatility on these 2 days, and I can give you the information that these are weekends, right? So you see in within these 5 days there is less volatility. The trend is slightly less. Like it's the y value is slightly low. The y value on weekends is a slightly high, but it's also really volatile, right? Within a particular day, for example, you see these peaks, these rises and ebbs. Um, these are basically just hourly seasonality, or sorry, the daily seasonality, right? So within each hour of the day, you see that the value of y is really different and it repeats itself over time. Um, so now if I'm trying to detect an anomaly during a weekday, do I really want to look at how my distribution looks like during the weekend? I don't. And this is easily verified here, right? So I know the behavior during weekends and weekdays is really different. I also know the behavior during certain hours of the day, you can call them, for example, prime hours, is really different than non-prime hours, right? So this for this here, like I think all you need to think about is just visually inspect and see what makes more sense. We're going to be doing a few simulations within this look back period, but you can, if you have your own data time series, all you can do is try different look back periods, see what works and what doesn't, and think about latency, right? So when I say latency, I say that because you're going to be doing this computation in a real-time pipeline time and again. If you're running this pipeline every minute, you're going to be calculating the means and the standard deviations of something every minute. Sure, sometimes it's so easy you can do it offline, but at other times you really have, for example, a rolling window that you need to compute things every minute. In that case, if latency is a huge factor, you might want to think about storing some of the data offline and then doing it really quickly. But let's run a few simulations here, right? So now let's talk about the first really easy choice, which is using the entire history as a look back period. So you have the simulated data set. I also simulate an anomaly over here. You see that my y value increased sharply over here, right? Um, we call this an anomaly for our purpose, right? And I look at the entire history of the data set to calculate my mean and the standard deviation, and I calculate the z-score. So the graph you see over here in red is the z-score. And now let's say I have a cutoff at 3. I say everything beyond 3 because I want to detect this anomaly, right? I look at this as a data scientist and I say, okay, I want to detect this anomaly. Let's keep the threshold at 3. Fine, you detect this anomaly and that's all good. But you also see that the z-scores over here are really close to that threshold. And so you're going to be getting a lot of false positives, right? These are false positives because technically all of this data that is here or that is here is not an anomaly at all. So if you have a threshold here, you're definitely going to be leading to a lot of false positives. Another thing that you can do is what I talked about initially, like using a rolling window. So now let's say you say, I want to look at the last 10 minutes to determine my mean and standard deviation. And the reason for that is I believe that my time series in the last 10 minutes will predict my, or is a good estimate of how my next minute should look like. Sure, that may be true. However, when you're working with anomaly detection, right, you have this anomaly and you try to simulate z-scores using that rolling window of last 10 minutes. You see, you have really volatile scores, right? This is a zoomed in plot of that anomaly period. The blue over here represents the actual data. The red graph over here represents your anomaly score. And you see that as soon as the anomaly begins, you see a sharp increase in your anomaly score, which is good, which is exactly what we want. However, you see that it also goes down and turns volatile. The reason for that is because as soon as the anomaly starts, you will be using the anomalous period to compute your mean and standard deviations. And what you're basically saying is that my next minute should look like a part of this anomaly as well. But that is not true. You know, your real data is not supposed to be anomalous. So you're basically biasing when you use such a recent window. Um, and now let's talk about something that we've discussed, like partitioning weekdays and weekends, right? What does that mean? It means that I'm going to be looking at weekends to determine what my distribution should look like in terms of mean and standard deviation if I'm predicting on a weekend. And if I'm predicting on a weekday, I'm only going to be looking at the weekday mean and weekday standard deviation. And you see over here, the data set that we have, the anomaly scores are pretty stable. For non-anomalous period, they're within a range. For your anomalous period, they sharply increase over here, right? It stays the same um, throughout your basically the entire anomaly period, right? So entire 30 minutes, you have the z-score, which is really high and it doesn't go down. Um, and you see that the differentiability between non-anomalous and anomalous scores is really high, which is exactly what we want. Because if the differentiability decreases, then you see a lot of false positives. But let's go back to the slide of z-scores, right? So one thing that we do know is that z-scores are not just, they can be defined in other ways, right? So for example, I don't want to define my average in just as a mean. If you take, like if you're familiar with your high school statistics, again, you know about mean, median, mode as three ways to define at least an average, right? So we can also define a z-score using a median based like a median as an average and then median absolute deviation as a spread. I'm not going to go into the details because I'm really interested in showing how they work in practice. But when you simulate these scores over the anomaly period, this is again a zoomed in plot, right? One thing you see over here is that your mean based z-score, which is this line in red, the blue graph is the actual y value you see, and the green graph over here is the median base score that we're going to be introducing. So you see that within the mean based red line over here, the anomaly score again increases sharply, but then decreases because the look back period in the simulation is 1 hour, right? So let's say you are using a look back period of 1 hour for this. Um, you see that the mean is actually going down, which is not really an ideal behavior. However, you see the median base scores, they're also decreasing. However, they decrease at a much lesser rate. The reason for that is because your median based, any measure that is median based is going to be very, very robust to outliers. And why this is really important is because if you have a real-time pipeline, you will have anomalous data getting into it, right? You cannot really label anomalies as soon as they happen and then ask your model to use just the non-anomalous period. That may not be possible all the time. So you want to use robust measures that actually capture your scores really well, which is where I think if you have a real-time pipeline, go with the median-based measures. But yeah, now let's bring it back together, right? So this is what I introduced in the beginning. Like if you have a very simple historical time series data, if it's simple and predictable enough, um, do all the things that we talked about, do z-scores that are median based, use a look back period, which makes sense, is not really like a rolling, very recent window because you will have anomalous data creeping in. And smoothing. So if you have a really volatile time series, right, you want to represent the score maybe as an average of the last five values. Um, it really depends on how volatile your series is. It's completely up to you. However, if you have like a really low volume sparse series, one thing that you can also do is do a time-based aggregation. For example, predicting every minute may not make sense for a really low volume series. You want to maybe aggregate them into windows of 5 minutes, 10 minutes, and so on, which will give you enough confidence in your anomaly detection, like anomaly detection tool. However, if you do have like more complicated series in which you want to introduce a forecasting method, NeuralProphet is a very easy method. You can also go with other frameworks. But once you have the forecasts, you get the differences between the actual data and the forecasts, and you can actually calculate or do all the things that we talked about in the last section about z-scores, all these techniques on differences instead of just your historical time series. And so, yeah, so basically, one thing that I want to talk about in the context of real-time pipeline, right, is that you have data continuously populating your systems. You will always have, like, if you have anomalies in your data, which is why we're talking about this, you will have anomalous data creeping in. Hence, this is why it's really important to use robust metrics, right? Obviously, the one thing that may come to your mind is why can't I just remove anomalous data as they come? Like, sure, you can do it, but it takes resources and it takes time to label all of this manually. Why is this important though? Because now let's say you have a real-time pipeline that is continuously running, right? We talk about the model development lifecycle in which you have a model, you predict, you have a feedback loop, which says, okay, this is a right prediction or a wrong prediction, and you retrain the model again, right? So, and what data do you retrain with? All of these questions are important in a real-time context. How often do you retrain your model? When you're retraining your forecasting model, for example, you don't want to forecast on on anomalous data, right? You don't want to tell the model that, okay, this is what an anomaly looks like. And so the model will have that information and obviously output garbage because it thinks that anomalous period is what is expected, but it's not, right? So you want to remove anomalies from your retraining as often as possible. How often, and basically use all the metrics that we've talked about to, like in the context of the algorithm. For example, z-scores, look back periods, smoothing to make your system more robust. But one question that may also come when you're building this pipeline is how often do you generate forecasts, right? You have a modeling framework, but do I generate forecast, for example, every minute or every hour, or how long ahead do I forecast for, right? So one thing is, because anomalous data may be populating your systems, you don't want to forecast every minute, right? You want to maybe have a buffer so that there is enough time for you to label those anomalies, right? So forecast frequently, but there is no need to, for example, forecast every hour or every day also, if it works for you. You can take your time, forecast 2 weeks ahead into the future, see if it's giving you accurate forecasts or not, and then use them as the expected behavior. But yeah, I guess that brings me to the end of the presentation. I have all the talk contents, all the code over here, and it has the slides as well. But yeah, feel free to ask any questions if there are.
Thank you so much, Shreya. It does look like we have a couple of questions in the Q&A section. Is it okay if I put
Yeah,
at least one of them on the screen for you?
of course.
All right, here's our first one.
Okay. Um, Yeah, it is pretty similar in performance. I think NeuralProphet does everything that Prophet can. It is, you can think of that framework as a superset of Prophet. So if you want to experiment with anything in Prophet as well as NeuralProphet, just go with NeuralProphet, and you can actually model the auto regression part with the neural network, right? So that's why it is pretty popular. But if you want to just do away with the neural network, that's like a simple parameter change in the syntax. So absolutely doable.
Perfect. Thank you. I do apologize, but we actually are out of time. And so if you have any additional questions, please pop them in the Discord for PyData, or we also have the lounge available through AirMeet. But thank you again, Shreya, for this wonderful presentation. Thank you for everyone for attending. And we hope to see you at some more sessions coming soon.
Yeah, thank you, everyone.